Hi everyone, today we're going to do some analysis of the mechanics of microphysiological systems. Scientists commonly test the effect of drugs on cells that have been grown outside the body, which we call in vitro. However, in the body, cells are in a soft and 3D environment. When we grow these cells on hard plastic sheets, they tend to behave quite differently, which can make it challenging to get results that predict the effect of drugs in actual humans. Microphysiological systems are a rapidly growing device category that try to replicate the environment in the body so that cells can behave more naturally. In this example, cells are grown in a sheet that has air on one side and liquid on the other to mimic the environment of cells in the lungs. These cells are also stretched to mimic the mechanical strains experienced in biological lungs as a person breathes. A recent paper from a company called Emulate demonstrated that microphysiological systems using human cells can be more accurate than animal testing when it comes to predicting the effects of drugs, because the biology of animal cells is quite different than humans. This improved prediction accuracy could save pharmaceutical companies around $24 billion per year. The US government recently is trying to move away from animal testing, making these microphysiological drug testing systems much more important and resulting in a predicted increase in market growth by around 15% per year. So if you're considering what industry to go into after graduation, this could be a great industry to consider. So I just mentioned that lung cells are exposed to cyclic strains, but heart cells experience an even more complex distribution of strains. The strains at the tip are nearly biaxial, while the strains in certain regions of the ventricles are nearly uniaxial, which means it's stretched in only one direction. Other regions of this heart experience strains that are somewhere in between biaxial and uniaxial. Our lab has developed a microphysiological system for doing in vitro mechanical stimulation that resembles the mechanics of the heart. We have two sets of vacuum chambers that induce strain in an elastomer membrane that we grow the cells on. By applying different pressures of vacuums to the different actuators, we can achieve strains that range from uniaxial to biaxial. We'll use this system to practice calculating stresses and strains. We're going to analyze these microphysiological systems using Hooke's law. If you're using the Mechanics of Materials textbook by Craig and Taylor, this content is covered in section 2.13. We need to use the generalized Hooke's law to find normal strains when we have normal stresses in more than one direction. These equations for generalized Hooke's law essentially add together the contributions from stresses in different directions. For stresses in the direction of strain, there's a positive relationship related by the Young's modulus. For stresses in the transverse direction, the resulting component of strain is negative and proportional to the Poisson's ratio. In this example calculation, we want to create strains that mimic a particular location in the heart, and I've chosen some kind of random numbers of 15% strain and 5% strain. So we'll find the stresses that we need to apply in order to stretch this cell culture membrane by 15% in the x direction and 5% in the y direction. In the second part, we're going to determine the thickness of the membrane after applying these strains. And the thickness of the membrane starts off as being 0.2 millimeters. The cell culture membrane has a Young's modulus of 300 kilopascals. That's really soft compared to most materials, which is what allows it to be stretched. As a comparison, rigid plastic might have a Young's modulus around 10,000 times higher, in the range of a few gigapascals. In our three equations for generalized Hooke's law, we have two materials constants and 6 variables. Often the best way to solve these questions is to write down all three equations and then to determine what variables we know and which variables do we need to solve for. We know the strains in x and y because those are our given targets. We know that there are definitely stresses in x and y, but there are no constraints or stresses applied in the z direction, so we can set that to 0. Since we know 3 of the 6 variables now, That means we have 3 unknowns and 3 equations, so we can go ahead and solve. We'll go ahead and we'll go through the math step by step, but of course you're welcome to skip ahead if you'd like. We can start by rewriting the equations for strain in the x and y, and then rearrange the equation for the strain in y to solve for the stress. We can substitute that back into our equation for the strain in x, which gives us an equation that has 2 known values and only 1 unknown. Finally, we can rearrange this equation to solve for our unknown value of the stress in x. This is what we call plane stress conditions, where we have stresses in 2 directions. For plane stress, it's pretty common to end up having a term like this that includes 1 minus the Poisson's ratio squared. So when it comes to putting numbers into the equation, we need to remember a few things. There are 2 common definitions of strain. The non-dimensional strain, which has units of meters per meter, and the strain represented in percent. People often use the percent strain because it tends to be a little more intuitive, but we need to use the non-dimensional strain in Hooke's law, which is why I've subbed in values of 0.15 for the strain in x and 0.05 for the strain in y. Next, I've left our Poisson's ratio as a question mark for now, because I wanted to ask what value would you expect to get for the Poisson's ratio of an elastomer. So in general, the Poisson's ratio for natural materials can be between 0 and 0.5 and depends on the bonding structure of the material. Liquids have a Poisson's ratio close to 0.5, which indicates that their volume stays constant as they deform. Elastomers are kind of like liquid polymers that have been cross-linked to make them behave like a solid. And they also have a Poisson's ratio very close to 0.5. Finally, this gives us 70 kilopascals as the stress we need to apply in the x direction. Doing the same thing for the stress in the y direction gives us 50 kilopascals, completing part A of the question. The most common mistake we see when using Hooke's law is that students sometimes use the uniaxial Hooke's law when they should use the generalized Hooke's law. As a reminder, our generalized Hooke's law becomes the uniaxial Hooke's law when the transverse stresses are 0, which we know is not the case in our device. If we were to do the calculations incorrectly by directly applying the uniaxial Hooke's law, we find stresses of 45 kilopascals and 15 kilopascals in the x and y directions. Comparing to the correct solution using the generalized Hooke's law, we can see that the uniaxial solution for the stress in the y direction is not just a little bit wrong, but it's off by more than 3 times. So it's super important to remember to use generalized Hooke's law anytime we have stresses in multiple directions. The second part of this question was to determine the thickness after deformation. We'll use the last equation that we haven't used yet, which is our strain in the z direction. Now that we have already calculated the stresses in x and y, we can directly substitute these in to find the strain in the z direction as being negative 20%. The fact that the strain in x and y add up to the same magnitude as the strain in z direction is not an accident. It comes from the fact that the Poisson's ratio of 0.5 indicates that the volume is constant. We've calculated the strain, but if we look back at the question, we can see that it's actually not asking for strain, it's actually asking for thickness, which has units of millimeters or distance. We can use our general definition of engineering strain as being the change in length divided by the initial length to solve for the change in thickness as being negative 0.04 millimeters. However, we're still not done because it asks for the thickness, not the change in thickness. So finally, we can calculate our thickness in the z direction as being the initial thickness plus the change in thickness, giving us 0.16 millimeters. So the membrane, as we stretch it, changes from 0.2 to 0.16 millimeters. So now we've finished the question, but anytime we're doing analytical calculations, we need to keep in mind what are the assumptions and limitations of the equations. For the generalized Hooke's law, the assumptions are that there's a linear relationship between the stress and strain, and a linear relationship between normal strain and transverse strain. Most materials are linear in the range of small strains, but become nonlinear at large strains. For elastomers in particular, the stress-strain equation at large strains can be approximated by something called the neo-Hookean model, which looks like this for uniaxial deformation. You can check that when the strain is very small, the neo-Hookean model can be approximated as a linear relationship. By comparing the linear and neo-Hookean models, we can see that they are very similar in the strain range less than about 10%, and become increasingly different at larger strains. For the strains up to 20% that we've been discussing, we might expect that our answers are a little different than what we would find experimentally, because our physical system doesn't quite align with the assumptions of our equations. So our key takeaways from today's mechanics analysis is that in vitro drug testing is a growing industry. Generalized Hooke's law is necessary when there are stresses in more than one direction. We also went over a reminder of the definitions of normal strain, displacement, and dimension, where strain is dimensionless or in units of percent, whereas displacement and dimension have units of distance like meters or millimeters. Lastly, when elastomers are deformed by large amounts, nonlinearity of the material's properties become very important.